Well, do you know what? I make it half past 7.
Yeah.
Okay. Welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. Tonight we have Samantha Lawler joining us from Saskatchewan, talking about Planet Nine or Planet Nine, discoveries in the outer solar system. That will be followed by Alan, who's going to give us a review of the sky in May. And a late addition to the programme is you've got me for 5 minutes talking about an old telescope, but that'll be a members only discussion. And it's hopefully you'll find it quite interesting. For those people joining us on on YouTube, you can stay in touch with us. Our website has a host of information. You can follow us on Facebook or on Twitter, and nearly all our talks since lockdown are available on our YouTube channel, and it's proving very popular right around the world. So that's great news. What have we got coming up? Well, for members on a Wednesday next, it's the Imaging and Observing Group. And then just for a change on a Thursday, just note, a Thursday on the 20th of May, with Professor Catherine Haymans talking about the dark side of the universe. Now, this promises to be I think, a very interesting meeting for a number of reasons, but I'll say no more. On the 4th of June, we're joined by Petri Visaran from South Africa, talking about the South African Large Telescope Observatory. And on the 18th of June, Tom Field joins us from Seattle to talk about spectroscopy and how we can all get involved using a simple grating and his software. And on the 2nd of July, we've got Professor Giles Hammond from Glasgow talking to us about asteroid light curves, although that title may change, but in essence, the talk won't. So tonight, as usual, questions, if you've got them and you're looking on Zoom, if you put them on the chat line, and Peter will ask you to read them out at the end. And we'll be looking for any questions coming from YouTube on the comments section, so please pop them there. And with that, I'll hand over to Samantha, and you can share your screen, Samantha.
Okay, I will share. Okay, so yeah, thank you for inviting me. I'm happy to be here virtually to talk to all of you. So I've been lecturing on Zoom for over a year now, so I'm pretty good at answering questions from the chat during my lecture. So if you're on the Zoom call and you have a question, please feel free to type it in the chat, and at an opportune moment, I will try to answer it. So I'm going to talk about Planet Nine and the small icy bodies that are orbiting in the outer part of our solar system. So I'm in Canada, and it's very common here to start off with a land acknowledgement. So I would like to acknowledge that I live and work and conduct my research on Canadian Treaty 4 territory, which is the homeland of the Nahiawak, Anishinaabeg, Dakota, Lakota, Nakota, and the Métis-Michif people. And a lot of the research that I've carried out, it makes use of telescopes that are on the summit of Mauna Kea, which is sacred to Indigenous Hawaiians. So I'm going to start off talking about Pluto, right? So Pluto is the original Kuiper Belt object. So I'm going to interchangeably use trans-Neptunian object, or TNO, and Kuiper Belt object, or KBO. They mean the same thing. They have sort of different historical reasons why they're used, but I think I use them kind of equally throughout this talk. So apologies for that. So Pluto was considered a planet, as I'm sure everybody here knows, for many years, because it was the only Kuiper Belt object that was known for decades, right? And over time, we've gotten better and better images of it. It's gone from being a single point to kind of a fuzzy dot to a resolved system of dots to a world, right? So the New Horizons probe flew past Pluto in 2015, and we got absolutely stunning images of what one of the biggest Kuiper Belt objects looks like up close. Like, is just blew my mind. Like, I've written entire papers about Pluto's orbit, but I hadn't put any thought into what it actually looks like, and it's beautiful, right? So this, this is one of my favorite images ever taken in astronomy. This is not a computer generated image, right? This is an actual picture of looking over the limb of Pluto, right? You can see there are mountains made out of water ice. There are glaciers made out of nitrogen ice. It's so cold that nitrogen is a solid. You can see very thin layers of Pluto's atmosphere. Pluto does have an atmosphere. And you can see the shadows across the surface. It's just absolutely wild to me. So zooming in a bit, there are these regions with very smooth glaciers, right? So that's telling us there's no craters there. That's telling us that these are being resurfaced, right? This is active geology on an icy body that is 40 degrees above absolute zero, right? It is really cold out there. And I love these really close-up pictures, right? You can really see the interface between the water ice mountains and the nitrogen ice glaciers. And what's really nuts is that they have these sort of like convection cells. Like if you imagine, cooking a pot of oatmeal or something, right? Like there's these borders that it's probably the nitrogen slowly convecting, and there's water ice mountains that are floating on top of the nitrogen glaciers. So it's really cool to think about, right? So we know that Pluto is a world with active geology and craters and mountains, but it's not a planet, right? And that is because there are, so it's on a weird orbit, right? It is tilted out of the solar system. It is on a very elliptical orbit. And also there are now many other Kuiper Belt objects that are known that are almost the same size as Pluto. So Eris is the first one that was discovered. That when it was initially discovered, it was, so we don't actually, it's really hard to measure how big they are when we first discover them, right? So Eris, when it was first discovered, was bigger than Pluto. It turns out that it's actually slightly smaller than Pluto, but it weighs a lot more than Pluto. Now we know. So Eris was the Kuiper Belt object that got Pluto kicked out of the solar system, because suddenly it was like, well, are we going to have like 20 or 30 planets, or are we just going to have 8? It makes a lot more sense to just have 8. So Pluto got demoted to dwarf planet. We now know about a dozen dwarf planets. So these are Kuiper Belt objects that are big enough to pull themselves into a round shape, but not big enough to clear their orbit. Okay, so during this talk, I'm going to be talking a lot about orbits. So just some terminology that I'll be using. Right, so I already talked about TNO, KBO, trans-Neptunian object, Kuiper Belt object. Those are all, I'm using those interchangeably. I'm going to be talking about the eccentricity of an orbit. So that's how elliptical it is, right? So a circle has an eccentricity of 0. A parabola, right? So an open orbit that doesn't come back has an eccentricity of 1. So Pluto has an eccentricity of about 0.24. I'm also going to be talking a lot about pericenter. So that is the point on an orbit that is closest to the sun. So pericenter and apocenter is the most distant point. You can remember which is which because it's perilously close. And the inclination, right? So how tilted is the orbit relative to the plane of the solar system? All of the planets in the solar system are in the same plane to within a couple of degrees. But Pluto, for example, is tilted by 17 degrees out of the plane of the solar system. And then semi-major axis, right? So how big is the orbit? So Earth has a semi-major axis of 1 AU. It has an eccentricity very close to 0. It's an almost circular orbit. Neptune has a semi-major axis of 30 AU, 30 astronomical units, right? So it's 30 times as far away from the sun as the Earth. The main Kuiper Belt is about 40 to 42 AU is where most of the Kuiper Belt objects are orbiting. But there are very distant Kuiper Belt objects. So Sedna is one of the most distant known Kuiper Belt objects. Its pericenter is at 76 AU, right? So it never gets closer to the sun than 76 AU, and at its most distant, it's more than 900 AU from the sun. For reference, just on how far away that is, so Voyager 1 has been flying away from the sun faster than a bullet for 43 years, right? And it's only gotten to 152 AU, right? So this is really far away. And then, way farther out is the Oort cloud, which extends to 10,000 to 100,000 AU from the sun, basically halfway to the next star. And we know about Oort cloud objects because we see them come in on very elliptical orbits once in a while as comets, right? And so they become easy to see when they get close to the sun and evaporate. So we know that, so that's kind of the extent of the small icy bodies in the solar system. So for this talk, I'm going to be focusing on the Kuiper Belt because that's what I study. That tells us a lot about the history of the solar system. Okay, so Pluto's orbit is kind of special because it actually crosses the orbit of Neptune, right? So it's not part of this main Kuiper Belt. It's in a special kind of orbit called a mean motion resonance. So this was first shown in 1964 with like punch card Fortran integrations on a big vacuum tube computer, right? And interestingly, so we're pretty sure that Dr. Gladys West, who, if you've seen the movie Hidden Figures, she was the one who actually did the computations for that to show that Pluto's in this special kind of orbit. But she was not given credit on the paper because back then you had a computer, a human computer, who would do the calculations for you, and they didn't even get credit in the acknowledgements. So women dominated the field of programming early on, which I think is kind of interesting. So now astronomers generally do their own calculations, and everyone is on the paper together. So it's nice to see that practice changing. Okay, so here is what Pluto's special orbit means. So on the left side here, we've got the blue circle is Neptune, the purple is Pluto, right? And so you can see that Pluto actually crosses Neptune's orbit. So why don't they ever crash into each other? And that is because in the amount of time that Neptune goes around the sun exactly 3 times, Pluto goes around the sun exactly twice. And so you can see this better if, so now imagine that you're looking down on this left side and you're kind of rotating at the same speed that Neptune is orbiting. So you're keeping Neptune in the same place. And now you see what Pluto is doing relative to Neptune. So that's what's happening in this plot on the right. And so you can see that every single time that Pluto gets close to the sun, it is as far away as possible from Neptune. And that's because there's this resonance, this orbital resonance that protects Pluto from ever crashing into Neptune. So this is a really special kind of orbit. And it's telling us something about the history of the solar system. So if you watch over, so now it's really easy to make an orbit simulation that lasts millions of years. And you can watch what happens over time. So here's, Neptune is again in that co-rotating frame being held fixed in one place. And this is what Neptune does relative to, what Pluto does relative to Neptune. And so over time, this closest point to the sun actually kind of wiggles back and forth, but it never gets close to Neptune, right? It's always protected over very long timescales, billions of years. So this is telling us that these orbits are kind of linked together. So this is 3 of the moons of Jupiter that are in these orbital resonances with each other, right? And so what happens is they're always in the same place relative to each other when they have their closest pass. So over on this side, so I've got position angle. So position angle is just like the angle around the circle, and semi-major axis and eccentricity, right? So every time the 2 planets or 2 moons, so we'll say planets in this case, the 2 planets have their close approach to each other. That means their orbital angle is the same, right? And so in this little diagram, they light up in a different color when they have their close approach to each other. And when that happens, they give each other a gravitational kick, right? So the semi-major axis changes a little bit, the eccentricity changes a little bit. So if we look at this over a longer time, so here you can see every time those 2 planets, the position angles cross, that means that they are having a close approach with each other. And so they're, giving each other little gravitational kicks. The orbits are changing slightly over time, but it's kind of random and just averaging out to staying in the same orbits. Now, when you have 2 planets that are in resonance with each other, right? So you can see by eye, it looks very different, right? You can see that this angle, their angle of close approach always happens at the same place. And that means that those 2 planets are coupled to each other. It's kind of like if you have, pushing a kid on a swing, right? Like if one of the planet's orbits changes, the other one will also change because they're kicking each other in the same place every time. So when you see orbital resonances, it means that these 2 planets are coupled together. They've moved together at some point in the past. So that was the initial theory to explain Pluto's orbit. Neptune started out closer to the sun and it moved outwards. As it moved outwards, it captured Pluto into this special orbital resonance and pushed it outwards, and they moved out together. So here is a computer simulation showing that. This is smooth migration. So looking down on the solar system, so these rings here are the orbits of the 4 giant planets, and then these little dots are Kuiper Belt objects from the very beginning of the solar system. And so this is called smooth migration, where Neptune slowly moves outwards, and it sort of snow plows up Kuiper Belt objects. Good Canadian analogy. Snow plows Kuiper Belt objects into its resonances in front of it. So we can make a prediction based on computer simulations like that, what the Kuiper Belt should look like. The initial theory for the Kuiper Belt was that it should be a low eccentricity, low inclination belt of leftover bits of planets, right? So I'm going to show a lot of plots like this. So this is semi-major axis versus inclination and eccentricity, right? So it's telling us about the orbits that are there. So Neptune would be like here, right, at 30, and low eccentricity, low inclination. So this is what we expected to see, what astronomers expected to find when they first started looking at the Kuiper Belt. And Pluto is already not in that part, right? It's already high eccentricity, high inclination. And as more and more Kuiper Belt objects were discovered over time, it clearly does not match the predictions for a low eccentricity, low inclination belt. It also doesn't match the predictions from smooth migration that we get from computer simulations. So another possibility, and more violent possibility, is what's called the Neis model. So same idea. This is a computer simulation. The 4 giant planets start in closer to the sun, and they orbit there for a few million years. And then there is an instability that causes the giant planets to scatter each other outwards. And that destroys the initial Kuiper Belt. But as Neptune sort of circularizes again, it traps a bunch of Kuiper Belt objects into mean motion resonances again, so orbital resonances. So there you go. So it just exploded and destroyed the initial Kuiper Belt. So this is another possibility. So from our computer simulations, we have predictions for what the Kuiper Belt should look like. From Nice model, from smooth migration, and then we have our data. But we have to talk a bit about observational biases, which are very important in the Kuiper Belt. So in the Kuiper Belt, so Kuiper Belt objects don't make their own light, right? They're not like stars. We depend on reflected light from the sun to see them. So light from the sun has to travel all the way out to the Kuiper Belt object. It drops off in brightness by 1/distance squared, and then it reflects back to us and drops off by another 1/distance squared coming back to us. So if you have a Kuiper Belt object that is on a very eccentric orbit like this, let's say it's 10 times farther away out here than when it's in close, it's going to be 10,000 times fainter when it's at its most distant point, right? So we are very much biased toward finding them when they're in close to the sun, but they spend very little time there, right? Because of Kepler's second law, they travel much faster when they're close to pericenter, close to their closest approach to the sun. So it's easier to find them, but they spend less time there. So that is an observing bias that we have that we need to think about. So, oops, I forgot to. So I gave this talk in Canada, and I was supposed to have. I don't actually speak French. I was supposed to have some French in there. So sorry, some of the slides I forgot to take the French out. I apologize. So this sort of brings us to the idea of Planet Nine. So Planet Nine is a theory that tries to explain the first 6 very distant Kuiper Belt objects that were discovered are all on very eccentric orbits, all kind of in the same direction. And so Planet Nine is supposed to be a giant planet that is really far away from the sun, like 500 AU. That maybe could explain these orbits that we see. But the problem is that you need to know where on the sky you looked to find these Kuiper Belt objects, right? Astronomers don't like reporting like, oh yeah, I looked all over this part of the sky and I didn't find anything, right? Like nobody likes reporting that, but that is very important information, right? So are all of these, you can see that they're all kind of, almost all of them are in kind of the same direction. They're their closest point to the sun, which is where we're most likely to find them. So did we find them all there because they're actually clustered or because nobody looked over here? And we don't actually know the answer to that. So the solution is to build a survey where we know exactly where we looked and we report all of that information. And that's what we've done with the Outer Solar System Origin Survey. So, so this is a large international team of astronomers, about 40 of us, led by Canadian principal investigators, to try to find lots of Kuiper Belt objects and be very careful about all of our observing biases. So we conducted this survey on the Canada-France-Hawaii telescope. This is on the summit of Mauna Kea, and it is a huge, so we used the megacam camera, which is huge, right? You can see compared to people's hands, like it's great for a wide field survey to try to find Kuiper Belt objects. So the field of view is a square degree on the sky. So that's great for just taking lots of pictures and trying to find Kuiper Belt objects over a wide area. The way that we find Kuiper Belt objects is exactly the same way that Pluto was discovered. It hasn't really changed, except now we have computers to help us, so we don't always have to look at every single image. So we take a picture of a spot on the sky, come back an hour later, take another picture, an hour later, take another picture, and see what moves between the frames, right? And the Kuiper Belt objects are actually moving because of the Earth's motion, right? Earth is moving much faster than these Kuiper Belt objects because we're in much closer to the sun. So because of parallax, we actually see them move hour to hour. So we made sort of blocks of megacam fields on the sky. And so for each of these blocks, so each of these squares is one megacam image, right? And so for each of these, and they together make sort of a block on the sky, where inside that block, we know how good a job we did covering the sky, right? You can see there are little holes, right? It's not perfect. We know how faint of a Kuiper Belt object we could have discovered, and we know how well we tracked all of the Kuiper Belt objects that we discovered, which we did a very good job of. So this resulted in 840 new Kuiper Belt objects. So for reference, before the survey, the Minor Planet Center database, which holds all of the small bodies, had about 2,000, and about half of those had been lost because the orbits were not well known. So we effectively doubled the number of known Kuiper Belt objects in one survey. And so this is, again, looking down on the solar system. And these little slices, these little pie slices, are the blocks through the solar system. And the blue dots are the real objects that we discovered. So you can kind of see their distribution there. So there are biases built in here, right? And every survey has these biases, but we were very careful to keep track of them, right? So in this direction is the Milky Way galaxy, and it is really hard to find small moving fuzzy dots in front of the Milky Way galaxy, right? It's just much harder to do. So we didn't even try to do it there. Let's see, I forget which is which, but so in one of these directions is winter on Mauna Kea, and the weather is terrible, so you're unlikely to get your observing time. The other direction is a large survey that was being carried out looking toward some particular cosmology target that I can't remember. And it's hard to get observing time there because they have a huge program, right? So all of these biases are built into every survey. There are biases like this, but we know our biases. So we can take our discoveries and debias them. We can find a model that is statistically consistent with our detections. And so again, the semi-major axis versus inclination and eccentricity. So this is the discoveries, and then this is the debiased version, right? So you find like one Kuiper Belt object out here. Those are really hard to find. They're really far away. We're really biased against them. So if you find one, that means that there has to be a lot of them that you did not actually see in your survey. And so we can say now that so each of these little tiny dots represents a real Kuiper Belt object bigger than 100 kilometers in size. We know there's 400,000 of them, right? So there's a lot of stuff out there that we've only found 3,000 or so total so far. So we have a lot of work to do still. Okay, let me pause real quick. Are there any questions? If anybody has a question, you can type it in the chat. Otherwise, I will keep going. Okay, so now we have to talk about Planet Nine. We have to talk a little bit more about these high paracenter TNOs. So these are the ones that never get very close to the sun. So here now we're looking at paracenter distance versus orbit size. So Neptune is like way down here for reference, right? Can any of these objects have the potential to form a planet? There's not enough of them in a small enough space. They're kind of dispersed. So not anymore. In the early days of the solar system, they could have maybe, but they didn't for whatever reason, possibly due to migration. We don't know for sure, but there's not going to be any planets forming out there in the present day. It's a good question. So all of these are, so this is from the Minor Planet Center database. So this is a great resource because it has all of the small bodies that have been discovered, but we don't know the observing biases that went into it. So there's a little bit of danger there. So these different types of orbits that we see on here, right, we can explain a lot of them, right? So, the main Kuiper Belt, we think that's where Kuiper Belt objects formed, and they just never got scattered away from that. Pluto, we think, was captured when Neptune migrated outwards. Eris gets close enough to Neptune that we can explain its orbit with gravitational kicks from Neptune, but Sedna never gets closer to Neptune than 46 AU away, right? Like more than the distance between Neptune and the sun. So it's not getting gravitational kicks from Neptune. So how did it form there? We do not know, right? And that's part of the why this is so interesting. So here's the same plot again, but now with a little bit more information. So the very distant Kuiper Belt objects, we can actually explain those orbits with tides from the Milky Way galaxy. Tides from the galaxy will actually change the orbits of the most distant Kuiper Belt objects. And down here, even though they never get closer to Neptune than 50 AU, we've shown with dynamical simulations that these ones, we can explain their orbits with very weak gravitational kicks from Neptune. But there's two up here that we cannot explain their orbits with any known dynamics in the solar system. So Sedna and VP 113. Okay, so the original Planet Nine theory, we'll go back to that again. All of these high paracenter TNOs that were discovered initially are aligned by a distant 10 times the mass of Earth planet called Planet Nine. So that's the theory. When you look at how they're selecting very distant objects, so it's sort of an arbitrary cut. They're just saying above some paracenter distance, we're going to say all of those are aligned by Planet Nine. But there's a lot of other effects that are happening in here. So, but that's how the initial theory was put forward. The other thing is that these six distant Kuiper Belt objects were discovered in 6 different surveys that we don't know the observing biases for. Right, so this is extreme unpublished observing biases that we have to be careful about. Okay, so what about OSSOS? We know our observing biases. So there are 4 Kuiper Belt objects that have high enough paracenters that they could fall into this high paracenter category. So are they aligned? So let's look at this. So here's this plot, right, showing the 6 initial Kuiper Belt objects at high paracenter. So now I'm going to show you kind of so this is from 2016, right? So rotate so that I can compare with a plot that I've made. So this is how many have been discovered as of late 2020. So you can see that, so there's still some clustering, right? You can see that there are definitely more high paracenter TNOs on one side of the solar system than the other, but there are a couple that are in the opposite direction, and there's one that's kind of like 90 degrees off, right? So, okay, so what about observational biases here? So OSSOS, so these are the 4 that were discovered by OSSOS, and you can see that they are really consistent, even without doing the statistical analysis, just by eye. You can see that that's pretty consistent with a uniform distribution. We see no evidence for clustering in our data that we have really good measure of the biases. So there is another survey that was done where they it's called the dark energy survey, because they piggybacked on a cosmology survey to try to find Kuiper Belt objects. And so they looked all kind of in one part of the sky. They discovered 300 Kuiper Belt objects, which is great. So they also kept very careful track of their observing biases. And so these are the 4 that they discovered. And again, so they only looked in the in the part that you would expect the clustering to be in. And they found kind of the extremes, right? Like almost 180 degrees apart. So they also conclude that they find no evidence for clustering. All of the clustering was just because of observing biases. There was just a couple months ago, there was another analysis that pulled together the biases from OSSOS, from this dark energy survey, and from another survey by Shepard and Trujillo. And so the white is kind of what orbits you're sensitive to. You can very clearly see the OSSOS blocks here, right? So we're looking down on the solar system again. And the red dots are the very high paracenter TNOs that have been discovered. And essentially what you can see here is that you discover them where you looked, right? Like any place on the sky that you were sensitive to them, that's where you find them. So there is no evidence that these high paracenter TNOs are clustered in any way. It's just observing biases. So now 3 separate analyses have come to the same conclusion. So how did this happen, right? Because so this is a theory put forward by a couple of Caltech profs. I had one of these Caltech profs when I was an undergrad there. They're very smart. Like, how did this happen that they missed the observing biases, right? And it's really hard. So this is the original 6 clustered TNOs. This is a simulation that I ran. So all of the black orbits are just randomly drawn orbits. And I said, okay, so what if I was observing from one telescope in Chile in the fall? What would I have discovered? And you get clustering, right? If you have any sort of biases in your survey, which every single survey has, then you will look, it looks like you have clustering. Okay, so let's go back to this plot again, right? Because I still haven't come up with any satisfactory answers for these high paracenter TNOs that have no explanation for their orbits, right? So adding a little bit more information here. So now the colors basically show you how hard is it to find these Kuiper Belt objects, right? So blue means it's really hard to find. Yellow means that you're more likely to find them, right? And that's just based on distance, how bright they are. So the thing that really bothers me is that there's these 2 that are really hard to find, and there's nothing discovered in this part in between these ones that are easy to find and these ones that are really hard to find. So why is that? So the purple points are the real objects, and then I've put down some simulations. The green points are a simulation that I ran with Planet Nine in the outer solar system to see what does the Kuiper Belt look like, what orbits are there out there. And so the green points are what you get with Planet Nine. And there are orbits that match these 2 weird ones, Sedna and VP113, but there's a lot down here. Why don't we see those? The rogue planet simulation is you stick a couple Earth mass planet in the outer solar system and have that orbit for a few 100 million years and then eject it from the solar system. And so that gives you the black point. So again, it's not quite as good at producing like Sedna, but there is a lot down here. So the ways of that have been proposed to produce these orbits produce a lot of orbits that we do not see. So what's the answer? And it turns out there's a lot of possible explanations, and we don't know which one is right at this point, right? It could be, there could be like anything related to an extraplanet. It could be these were captured by a close pass with another star system early in the solar system's history. These are Kuiper Belt objects captured from somewhere else. It could be caused by a close flyby from a star. Diffusion, just weird orbital changes from the inner Oort cloud, which we don't understand very well. It could have something to do with during the migration process as they fall out of resonances that they've been snowplowed into, right? So there are a lot of possible theories. And Planet Nine is just one of those possible theories. So the answer is that we need to find more, right? We have a lot, but we really need to find them and find them in surveys where we understand the observing biases. Otherwise, we'll find some kind of clustering that is maybe not there. So the OSSOS is done. We're not going to redo that. But LSST is coming. So the Vera Rubin telescope is the first light is scheduled for 2022. I'm not sure if that's going to be delayed because of COVID, but construction is ongoing. So this is an 8-meter telescope that's it's being built in Chile right now. This is a fairly recent picture of the dome being constructed. And so it's going to discover thousands more TNOs. We will still need targeted surveys to try to find these most distant, hard to find high paracenter TNOs because they're really faint. They're actually going to be too faint for this survey to find. But the aggregate of finding thousands more and a few targeted surveys, we will get some good answers to test how these most distant Kuiper Belt objects were placed on those orbits. But in the meantime, the American private company SpaceX is in the process of launching batches of 60 satellites into low Earth orbit every 2 to 3 weeks. There was just another batch a couple days ago. So there's currently almost 1,500 Starlinks in orbit. This is 33% of active satellites, and they were launched within the last year and a half. By the end of 2021, SpaceX will control 50% of active satellites, right? It's just absolutely mind-blowing how fast they are launching these. And there is no regulation on this, right? So this is from a recent paper. This is Starlink proposes to have 12,000. They've already got permission to launch 12,000 satellites. They plan to expand to 42,000. So actually you need to multiply these dots by 3.5 in order to get to the final numbers, right? So, so this is a lot of satellites all together. So this is a calculation of the number of Starlinks above the horizon by latitude at any given moment. But you need to multiply by 3.5 if they actually go to 42,000, right? So most of Canada's population is right at this. So the blue is the total, right? So, hundreds, thousands of satellites above the horizon at any given moment. So you guys are about here, right? So you're on the downside of it, but you're still, that'll be a couple thousand satellites above the horizon at any given moment, right? Not all of them will be visible, but many of them will be. So these are calculations for 52 degrees north, so a little lower latitude than you. But this will be similar. So during the summer, at any given time during the night, there will be hundreds of them illuminated all night long. In the winter, you at least get a little bit of darkness, but close to sunrise and sunset, there will be hundreds of them visible for a couple of hours. So, we've seen, probably all of us here have seen Starlinks now. It's particularly bad in long time exposures because so many of them fly through in a line, right? So it's going to be extremely challenging for naked eye astronomy and for professional astronomy. So SpaceX is, so after a lot of yelling by astronomers, they have stated that they're going to try to get them down to 7th magnitude, which is below what you can see with your eyes, right? But current measurements of even the satellites that have been darkened, that have sunshades on them, the darkest are only about 6.5 magnitudes. So they're still naked eye visible. We're looking for TNOs that are 25th magnitude, right? So that's 15 million times fainter than this, right? So this is a science image from CTIO. You can see, so every single chip that one of these has flown through, that's dead. Like you're not going to recover any science data from those chips. So there's maybe like one or there's a handful of chips that didn't have a Starlink fly through. So the Vera Rubin telescope estimates they're going to lose 30% of their observing time because of this easily. So this is bad, right? Like particularly for the kind of wide field astronomy that I do, this is devastating. And SpaceX isn't the only one. That's the really terrible part. So SpaceX is the first one, but there are many other companies that are planning to do this exact same thing. There are no rules about light pollution by satellites. There are no rules about orbits or right of way. We're in very real danger of Kessler syndrome. The only international laws that apply to satellites are from the 60s, from the space race. So this needs to be updated at the UN level. There are committees in the UN that are working on this. I am meeting with the government of Canada in a couple of weeks to talk about recommendations for how to possibly mitigate this, but countries that are not launching states don't have much power here. So in particular, trying to change the liability rules, because right now, according to the treaties from the 60s, if SpaceX dropped a satellite on my house and killed me tomorrow, then my family could not sue the company. The government of Canada could sue the government of the US on my behalf, but that's it, right? There's no private companies in these rules. It's entirely it's written from in a time when governments were the only launchers of satellites. So that needs to be addressed as soon as possible, or we will lose the night sky. It's already quickly being lost. So, okay, so sorry for that depressing rant. I'm sure most of you are aware of this, but it deeply affects all of us, right? So just to sort of wrap things up, so the Kuiper Belt is an excellent window into the planet formation process in our solar system. We've learned a lot about the Kuiper Belt through space missions, like to Pluto. We learned a lot from telescope observations, and a lot of what I do is with computer simulations. And this has taught us that the giant planets migrated. They formed in a different place than they are in right now. My research has showed that Planet Nine doesn't need to exist to explain the orbits that we see. It's probably due to observing biases. And there's a lot left to discover in order to explain some of the orbits that we don't know how they got there yet. So I encourage all of you, I'm sure that you all are taking advantage of this, but go out and look up as much as you can, because it's about to change. So yeah, thank you very much. Yeah, I will be happy to answer some questions now.
Well, thank you, Samantha. Can members thank Samantha in the usual way, please? It might be a long way away, but we can still applaud an excellent presentation. The four things for me: the perils of scientific research are often about what you don't know and understanding what you don't know. I think you illustrated that very well. Also, the explanation you gave of scale, I thought was particularly clear, and that was brilliant. Thank you very much. I was rather saddened by the expression fossilized resident dropouts. I suspect I resemble one of those. I would say that we're hoping in June to have an event to co-host with Edinburgh University, where Andy Lawrence, who has written a book, Losing the Sky, it's all about megaconstellations, where there'll be a panel discussing these very subjects. So we're really right behind that effect, and we've witnessed it sadly greatly recently, and it's, as you say, only going to get worse.
Yeah.
So we'll certainly forward you the details of the what is likely to be an international discussion on mega constellations. Okay, have we any questions, Peter?
We've got a couple of comments from John and a question from Carol. So, John, did you want to highlight your comments? Or?
Hang on, I'll remember what I say now. Really, it was about one of the problems at one of the meetings to discuss these satellites was that something for like LST is that they're so low that they're not in focus. So instead of getting a nice, neat 1 pixel wide band that you can get rid of, you end up with the sort of Gaussian smeared out bit of rubbish that you can't actually get rid of. So all your photometry falls to bits in. So the chances of professional observatories apparently getting rid of them is fairly low.
Yeah, it's, well, and then a telescope like the Vera Rubin telescope, it's an 8-meter telescope, right? So it's gathering a lot of photons at once. So so a lot of it is just overloading the pixels, right?
Yes.
So that's a lot of the problem. I know that there are astronomers who are working on machine learning algorithms to try to salvage some of the data from chips that have satellites pass through them. This is something, you know, we might be able to come up with some kind of algorithm. It's also important for satellite companies to share positions of satellites, right? We might be able to do some sort of pointing differences, right? The thing that actually concerns me much more, like, I'm deeply sad about the loss of science, but I'm more sad about the loss of the, you know, just looking up and seeing the stars, right? Like, that is much more concerning to me. There's no machine learning algorithms to fix your eyeballs, right? Like, yeah. So, yeah, you're right. There's just a lot of problems with it.
And my other comment was about radio astronomers, because of course they're broadcasting 24/7.
Yep.
And I was reading a paper yesterday that said one of the surveys is losing 90% of their data now when they look in the direction of the geostationary satellites.
Yeah,
when you've got all these Starlink satellites as well, radio astronomy from the ground is going to be pretty difficult.
Yeah, and yeah, I was very focused on optical astronomy because that's what I do. But yeah, radio astronomy is even more in trouble. And there will be, like, it depends on how the I haven't heard from radio astronomers specifically. I mean, they must be seeing noise from Starlinks now. There's just so many of them, right? So I don't know how bad it is. There's a like you mentioned with the geosynchronous satellites, there's one, I forget which one. There's one particular constellation of satellites that was really terrible. It, like, wiped out some specific frequency that a lot of astronomers use for studying star formation or something.
Yes.
And so there's a lot of parts of the spectrum that will just be unavailable to radio astronomy. And yeah, and there's no regulations on that, so it's unfortunate.
That's right. Well, I think
John, can we move on? We've got a few questions. We've got Carol first, and then John Davis.
Right, it's Carol here. Thank you very much, Dr. Lawler, or Professor Lawler. I'm not too sure to call you Professor or Dr. Lawler, but thank you very much.
Either is fine, thank you.
It was an excellent presentation. The question I have is about bias. You talked a lot about that in your talk. Could you have, if you had an infinite amount of telescope time, could you have telescopes and you hadn't got satellites in the way? Could you just use telescopes in the northern and southern hemispheres, and would that avoid, you know, some of the biases anyway?
Yeah. So there is some getting, like, LSST, right, will be observing the entire night sky every 3 days, right? But there's still some biases built in, like the Milky Way, right? It is really hard to find Kuiper Belt objects in front of the Milky Way, no matter where on Earth you're observing. That's just because there's more background stars. And weather, you'll still be limited by weather. It might be different limits in different places, but there will be times of year where it's harder for you to observe the sky perfectly. So there is no way to remove all the biases. Even if you were to go to space, there will be other biases, like, oh, well, I can't look toward the sun, right? Like, you're never going to get rid of all of your biases. There's there's going to be something no matter what. So you always have to think about this when you're designing a survey.
Okay, thank you.
John Davis, please.
Yeah, thanks. Yes, I don't want to turn this into a Starlink bashing session, but in fact, John's right about the trails being out of focus, but LSST has another problem, which is that the detectors are non-linear. So these bright trails cause parallel ghosts, which are very hard to eliminate. And also any elimination algorithm you use will introduce its own biases. So for those people, I mean, I'm not one of them. We are not one of them, because I'm not interested in galaxy lensing kind of things. But if anything that relies on a smooth background will be totally damaged, even by the removal algorithm.
Yes.
So yeah, I mean, I've got Andy's book, and I'm in an RAS working group on this. I've just written a report to the RAS.
Oh, good.
We've got a Zoom on Tuesday next week. The radio astronomers have also been asked to write to me, but they haven't done it yet. And again, and John is right, the radio people have got a much bigger problem, because for us at least, the satellites aren't that visible at midnight in winter, because the sun's below the horizon, it's a long way below the horizon. But these radio things are broadcasting constantly. Right, okay, end of Starlink rant. Thank you very much for the talk. As I said at the beginning, I'm an observer of these things. I'm interested, are they blue or red, and are they round, and are they spinning? But I've spent a lot of time talking to dynamicists to do exactly what you do, which is chuck millions of hours of computing at them and model 500 million years of evolution. It's great. It's far too difficult for me.
Thank you. Yeah, and thanks for fighting against megaconstellations. Every little bit helps.
Any more members' questions, or shall we move on to Will?
Yep. Thank you, Professor Lawler. That was absolutely amazing talk there. I'm just picking out a selection of questions from YouTube. Been lots of good comments flowing about your wonderful talk. So we've got from Stephen Schreier, could a brown dwarf object be one possible explanation for planet Nine? And he also mentions, or Schreier also mentions, do you think that the possibility of lots of these satellites may need to be deorbited in future times?
Okay, yeah. So two very different questions. So there are other possibilities for what Planet Nine could be. I actually saw a published paper saying, what if it's a black hole? If it was a 10 Earth mass black hole, and then that paper, it was a published paper. So, when I publish a paper, I spend so much time like meticulously making the plots perfect and everything. This had a plot of a black circle about this big. Like, this is how big Planet Nine would be if it was a black hole, right? So obviously that would be hard to find. Also hard to explain how it got there. But there have been papers looking at the possibility of it as a brown dwarf that is really far away. And I think that has been ruled out by radio data. There have been papers looking at lots of possibilities for brown dwarfs. But I think those are mostly ruled out. It has to be something that is smaller than, I think, Saturn or so. Brown dwarf would be many times the size of Jupiter. So good question. And okay, so deorbiting Starlink. So that's another thing. This is another one that like keeps me up at night. So Starlink, their plan is to deorbit their satellites kind of continuously every 5 years. So each satellite only lasts 5 years. So that is a huge amount of mass being deposited in our upper atmosphere. And they're very proud of the fact that they make their satellites so that they burn up completely in the atmosphere, so there's nothing left to hit the ground. But that means that all of it is being deposited in the upper atmosphere. They're mostly aluminum. So if you do the calculation, so if there's 42,000 satellites and they're replacing them every 5 years, that's 25 satellites a day that will be burned up in the upper atmosphere. That's enough aluminum to potentially change the climate of the planet, right? Like that's one of those last ditch geoengineering, try to save the planet ideas, is to put aluminum in the upper atmosphere. And a lot of people have been kind of terrified of the effects of that, right? So SpaceX is going to run this experiment for us without any consultation. So that's something to think about that nobody has really talked about much.
Wow, that's quite an incredible prospect that we're going to face.
Yep.
Moving on from Stephen King, is there a gap between the Kuiper and Oort cloud, and if so, why?
Okay, so that's something we don't really know the answer to that, right? It is really hard to find the distant Kuiper Belt objects. It's really the only reason that we know about Oort cloud objects is because we see the ones that are on very eccentric orbits that come screaming through the inner solar system as comets, right? So we don't really know a lot about the orbits that we can't see, right? Like there's just no way to see them. Most of what we know about that is from computer simulation. So that's an excellent question. We don't know the answer.
Wow. And then one final one from Miss Julie, just really asking what you feel. Did you find it interesting that scientists are finding water on other planets? You know, it's just a different kind of question. So
yeah, finding water on other planets that's like so I taught in an astrobiology course this year for the first time and totally loved it. Oh my gosh, I love astrobiology. It's so fun. But like one of the keys to life is water, right? Like there might be other solvents that could possibly work, but we're pretty sure that water is the only thing that life absolutely needs. So any life anywhere. So water is such a great, that's why astronomers obsess about it so much, like trying to find water in the atmospheres of exoplanets or on Mars, right? Like probes have found water on Mars how many dozen times now in different ways, right? Like, and that's important, right? That's telling us that there is a possibility for life when you see water. So I get very excited about it. I'm not sure if there was a specific question, just sort of general, if that's a good enough answer for you.
Absolutely. No, that absolutely. Yeah. Thank you.
Okay.
Thank you. It's that's us done from YouTube. Thank you.
Excellent. Well, again, if we can thank Samantha for her time, that was brilliant. Thank you very much indeed.
Thanks, everybody.
Enjoy the rest of your day.
Okay, thank you very much. Okay, bye.
Bye.
Thank you.
Okay, we're going to hand over to Alan now, who's going to take us through the sky in May.
Right, thanks, Andrew. Right, let's see. Can you see that?
Yes.
Yeah. Good. I'll just bring up my control screen, turn on my laser. You can see that, presumably. Okay. The sky in May this year. This is a very nice image taken by Pat Devine of the ASE of the Heart Nebula in Cassiopeia. The main glow in this nebula comes from ionized hydrogen gas. The nebula's 7,500 light years away and was discovered by William Herschel. And it's quite large on the sky. You could fit 5 moons across its diameter. But it's very dim, so you need an image to see it or a decent telescope. Cassiopeia is below the pole in the north tonight, and this nebula is located about 5 degrees to the left edge of the W of Cassiopeia. There's another slightly smaller, similar nebula nearby called the Sol Nebula, together the Heart and Sol nebulae. And the star clusters in here are giving this bluish glow. Okay, back to the usual introductory slide, the 2 views looking north and south at these times, about midnight BST in the middle of the month. The Heart Nebula is there to the left of Cassiopeia. The plough has now passed overhead by these times, and it's now starting to fall down in the western sky. Leo is sinking lower in the west. The summer triangle is back. Deneb, Vega, and Altair are climbing in the eastern sky and will become ever more prominent over the summer. But the only planet at these times is Mars, which is down here in Gemini. Yes? Seem to have got a dog on the line. Okay, take a look at the ephemeris for the sun this month. Draw your attention to this area of this table, showing that we're losing the dark sky the sun is dipping less than 18 degrees below the horizon, below our northern horizon in the middle of the night. So we're already, or we will be by August, a few days ago, into the region when we don't have any proper darkness, any proper astronomical darkness in the night. And we're also losing nautical twilight, which is what I define as effective darkness. We lose nautical twilight until the 11th and 12th of July, and we won't see astronomical darkness again until the 8th or 9th of August. And this is from Edinburgh, of course. This also means that the shadow of the Earth overhead is quite shallow, so that any satellite that's in range above our horizon is also illuminated by the sun and therefore visible. The moon, well, there's the phases of the moon, where the moon is currently a waning crescent, but it rises less than 30 minutes before sunrise tomorrow for Edinburgh. We might see it again on the 12th of May, just after new moon, when it's 2 degrees below Venus, but only 1% illuminated in our evening sky, probably very difficult to see just after sunset in the west-northwest. Better on the following few days when it'll be brightly earth-lit. Get rid of that. Is that, can you see a Ramsey thing? We'll get rid of that. Okay. One thing to bear in mind this month is that there is a total lunar eclipse corresponding with full moon on May the 26th, but we can't see it at all from Edinburgh. If you're in around the Pacific Ocean, then you can see that.
The Pacific Ocean.
There's the timing for the eclipse and the path of the moon through the Earth's shadow. The penumbra is the outer shadow of the Earth, where if you're in it, you can see something of the sun. From within the umbra, you don't see any direct sunlight from the sun, and the moon fades away, is much fainter. These times are UT, not BST, they're UT, but since we can't see from Edinburgh, it's not a great deal of interest to us. A few pictures of the moon taken by members this last month. We've had so many pictures on our Flickr group, there's no chance of me showing them all in this talk. Fran Goodman got this daylight image of the moon on the April the 21st. Mark got this nice image showing Plato, the crater, and the Alpine Valley on the same evening, the 21st of April. Ian Smith produced this view of the waxing gibbous moon on the 25th of April. There's Plato. And Mike McGovern got this image of the straight wall, this dark line on the moon, a sloping cliff in the Mare Nubium, the Sea of Clouds. The cliff is only around 230 to 300 meters high, which is the same height as Arthur's Seat, but it's 120 kilometers long. It's the best lunar fault line in Mare Nubium. It's about there on the moon. It's also called Rupes Recta, which translates as straight fault. And it's said that earlier British observers called it the railway or the railroad, but I've not really heard that before. As far as the planets in the sky this month, this stretches the sky across 360 degrees. The sun is here, and that's the track of the sun during the month. Still edging northwards towards our summer solstice position. Venus is a little bit east of the sun, and that's the view of Venus on May the 16th, quite a small disk. Mercury is above and right above left of Venus in our evening sky, and it's fading quite sharply during the month from magnitude minus 1.1 to plus 2.9 during the month, and growing larger in apparent size than Venus. Mars is a bit further from the sun. That's the view of Mars on May the 16th, even smaller than the previous two planets. And in the morning sky, we've got Saturn and Jupiter, both low in our southeastern sky. I'm going to change the habit of a lifetime now by beginning with the morning sky, 1 hour before sunrise. This is the Stellarium's view of our southeastern sky, 1 hour before sunrise on the beginning and middle and end of the month. And you can see Jupiter and Saturn getting higher at this time as the month goes on. This line is showing the line at 10 degrees altitude. So you can see that on the beginning of the month, Jupiter was less than 5 degrees high an hour before sunrise, rather hard to see from our latitudes. But by the end of the month, it's more than 10 degrees high. And both Jupiter and Saturn are quite well placed. Also, at the end of the month, you'll notice that the moon is below Saturn, 5 degrees below Saturn. And there's a view of Jupiter and Saturn. The moon is 5 degrees below Saturn, and that's the phase of the moon. That's what the moon will appear like on that morning, the 31st of May, 72% sunlit. And sticking with the morning sky, this was the view looking southeast yesterday morning at 4 o'clock BST. The reason I've chosen that time is that that's the predicted time, or close to the predicted time, for the peak of the Eta Aquarids meteor shower. The radiant of the Aquarids is quite low down from our latitudes. It's down here around 10 degrees northeast of Jupiter. And meteors are seen in all parts of the sky, but they stream away from that radiant. And there are the details for the shower, like the Orionids later in the year. These are debris from comet Halley, active until May the 28th, active throughout the month, more or less. The peak on the morning of May the 6th, they're fast meteors and they leave glowing trains in their wake. They've got a quite high hourly rate, but to get that hourly rate, you need the radiant in the zenith, and it's far from that from our latitudes. So it's definitely best visible from the southern hemisphere. Turn to the north at midnight BST, in the middle of the month, and the overhead point, as usual, is towards the top of the diagram. Here's a plough tumbling westwards, Polaris, the W of Cassiopeia, and the top two stars of the summer triangle, Deneb and Vega, over towards the east. Now, a couple of months ago, I mentioned in one of our imaging group meetings, I mentioned a nova that had been discovered between Cassiopeia and Cephus in this region, and I showed you this diagram, which showed where the nova is, in line with these two stars, Shadar and Kaf in Cassiopeia. That's the position of the nova, and that's an expanded view of that area using Stellarium. It was discovered by a Japanese amateur astronomer on the 16th of March. Initially, it was spotted at magnitude 9.6, but it brightened quite quickly to about magnitude 7.5 by the 20th of March, which would mean that we needed binoculars and a dark sky to see it. Before the explosion, it was probably a magnitude 15 and very dim through a telescope. There are around 50 novae a year in our galaxy. Most of them go unobserved. One last July reached magnitude 3.7 in the southern constellation of Reticulum, 55 degrees south of the equator, so never seen from Scotland, though it was discovered by a Scottish observer, Robert McNaught, in Australia. The brightest I've ever seen was in Cygnus back in 1975, at the end of August, when it flared to magnitude, that nova flared to magnitude 1.7. So it's just a bit fainter than Deneb, but it faded quickly below naked eye brightness within a week or so. And most novae do fade quite quickly. But by chance, Ian Smith imaged the nova on the 9th and 10th, night of the 9th and 10th of April. Here's the bubble nebula he was aiming at. This is a cloud of, again, glowing hydrogen, also called NGC 7635 or the Caldwell 11 object, created, and the bubble in the nebula was created by the stellar wind from a hot central young star, and it lies around 7,000 to 11,000 light years away. Well, here's the nova. What makes a nova? It starts off as in a binary star, pair of stars in a tight orbit. One of the stars has evolved to be a white dwarf. That's this one. It's thrown off its atmosphere to leave an Earth-sized body, a mass similar to the sun. And it's now the turn of the companion to get old and start at the end of it, or reach the end of its normal hydrogen burning life. It's swelling to the extent that material is flowing from it into an accretion disk around the white dwarf and settling onto its surface. Now, when that new material, that new hydrogen, reaches a depth of only around 200 meters, a bit deeper than North Sea. When it gets to that depth, there's enough pressure inside within that disk, within that layer, for nuclear fusion to occur, and a nova erupts. Spectacular brightening of the pair of stars. So it's not a new star at all, but a star that suddenly brightens. It flares usually for a short time, and then the process starts again. It settles down, and more material settles on the white dwarf, and we can get a repeat nova in a few years or centuries or millennia. So what's happened to our nova? Well, this is the light curve of Nova Cassiopeia. Here's the initial brightening to around 7.6, 7.5. It then faded quite slowly, and then it started to brighten again. And the latest observations just in the last day show that it's reached magnitude 6.6, which is right on the verge of naked eye visibility. This is unusual for a nova, but it's not unique. It reminds me of Nova Delphini, which I remember observing back in 1967. That nova was discovered by the English amateur astronomer George Alcock in July of 1967, when it was magnitude 5. But it didn't reach its peak magnitude of magnitude 3.5 until mid-December that year, 158 days later. So if this nova follows a similar pattern, then it could yet reach naked eye brightness, brighter than magnitude 6. Just have to keep watching. The star seems to correlate with the 15th magnitude eclipsing variable star with an orbital period of about 9 hours. Light curve of Nova Delphini 1967 is here, and these are in years, not days. This is its initial brightening in 1967, and you can see the behavior of the star's brightness over the following year or so. And this is its peak in December 67. So we need to see whether the Nova Cassiopeia follows the same scheme. Now to our evening sky. Well, this is the view 40 minutes after sunset at 8 days apart, May 1st, 9th, 17th and 25th, showing Mercury getting slightly higher and then falling back down again towards the sun. Venus throughout is getting a little bit higher with each day, but not very, very high. Mercury starts off on the far side of the sun, but it comes around, and when we lose it by the end of the month, it's on the near side, and there's a thin sliver. It reaches its greatest elongation of its distance from the sun on the 17th of May, when it's here above and to the left of Venus. Venus is lower down, set 64 minutes after the sun tonight on the 7th, and 93 minutes after the sun on the 31st of May. Still on the far side of its orbit, quite small. Mentioned before that the moon is 1 degree, sorry, the moon is 2 degrees below Venus on the 12th, and it's also 2.7 degrees below left of Mercury on the 13th. So chance to get those planets in the same image. This is a bit later. This is again midnight, looking west in the middle of the month. The plough is here, high in the west. Leo is in the west-southwest. Castor and Pollux side by side in the west-northwest. The two brightest stars here are Capella in the north-northwest and Arcturus fairly high in the south. And those are the two brightest stars on the chart. I want to take a look at this particular region here because that includes Mars and Gemini. Here it is, along with the path of Mars from the 1st of May to the middle of June. So during May, it's passing right through the body of Leo. Mars, I showed you this before, is very small, only 4.4 arc seconds wide in the middle of the month. And more or less full phase, though, even if you've got a telescope, you'd be hard pressed to see the phase or any detail on the surface. The moon is 3.5 degrees below and right of Mars on the 15th. That's the view on that night at 23:35. And I've chosen that time because the moon at that time is very close to a star Epsilon Geminorum, which it's about to occult. The moon's that's the what the moon will appear like. And on that night, we will see some Earth shine on the darker half of the moon, darker side of the moon. And if you want to watch an occultation of a star, that's the night to choose. It's about the best occultation to view this year, Epsilon Geminorum Mabsuta. But although it's a naked eye star, you're best to watch it through a telescope, because the moon's, even though it's not a full phase by any means, its light will be enough to drown the stars, certainly with the naked eye and possibly also with binoculars. So an occultation, rather brief, from 2336 to 2357 BST on the night of May 5th, the evening of May 15th. So watch for that. A couple of images of the Earth-lit moon. This was the moon on April the 14th, taken by Andrew, and the crescent moon taken by Peter Black on the same night. Actually, I think that should say April the 15th. I think it's because on April the 15th, the moon was 12% illuminated. So I think that's 14th and that's 15th. Looking south, the wider view again, looking south with Arcturus, more or less on the meridian and quite high up, 55 degrees, 53 degrees high, as seen from Edinburgh, and Antares in Scorpius, climbing up in the south-southeast, Leo in the west, or the west-southwest. Let's take a look at this particular region. And I'm afraid this is a bit more Starlink bashing, because I want to show you an animation of this region of sky. I'm going to watch it. I'm going to play it for 10 minutes of animation, but I'll speed it up. So it's, sorry, 5 minutes of animation. I'll speed it up so it lasts 30 seconds. And I'm going to ask you to look out for satellites, including Starlink satellites. Start, if you don't mind, by looking in the top right corner, because there are 3 objects here, 1 there and 2 here, which you'll see moving as soon as I start the animation. These are not Starlink satellites. These are secret US spy satellites belonging to the NOSS system, a Naval Ocean Surveillance System. And the Americans keep the orbits for these satellites secret, and we only know where they are because amateur satellite trackers are keeping track of them. But as I start the animation, you'll see those 3 satellites moving, 2 of them going off to the north, and the other one down here, which is actually a rocket heading off down through Leo. And here we go. And I hope your bandwidth is enough to see this animation. 2 satellites moving off, and this one coming across. And if you watch carefully, can you see other ones moving across the sky? Fainter satellites. These fainter ones, nearly all of them, I think, are Starlink satellites. This is from Stellarium, and you can run this simulation yourself with Stellarium, and you can identify all the individual satellites you can see. But I couldn't find any that were not Starlink satellites. There's one down there too. And this is only an animation for 5 minutes, and that's it, finished. As we've mentioned earlier, Professor Andy Lawrence, our honorary president, has produced a book, Losing the Sky, in which he discusses the problems caused by satellites. There were another 120 Starlinks launched in the last 8 days. And by my reckoning at the moment, the total is now 1,474. So the problem is not getting any better, it's getting much worse. Anyhow, let's look at that same area. And Ian mentioned last month a comet. I don't normally mention faint comets, but Ian mentioned it. So I thought I'd bring you an update about it. This is Comet Atlas, Comet 2020 R4, expected to be quite dim. In fact, this plot from Stellarium shows the predicted magnitude in brackets following these dates as it moves along this part of the sky. So even at the beginning of the month, it's magnitude 13.68, it says. And it was closest to us on April the 23rd when it passed 69 million kilometers from the Earth. But it could well be 5 magnitudes brighter than predicted here, based on an image taken by Denis Buksinski of the BAA on the 29th of April. He's showing the comet around 8th and 9th magnitude. And he reckoned that there was a An outburst began of the comet between April the 20th and April the 24th. And I just learned about 3 hours ago that there may have been a further outburst of the comet yesterday. So it's, if you can find it, it might be worth looking at. Of course, the increasing twilight means imaging comets falls in the same problem as imaging nebulae of galaxies, because the twilight will swallow up these objects quite quickly. This is another image of taken on April the 30th by Michael Jaeger in Austria, showing Comet Atlas up here, and not far away, another comet, Comet Palomar. Comet Atlas was at perihelion on the 1st of March, and it may be in an orbit of around 930 years. The Comet Palomar reaches perihelion on July the 11th, and its orbit may last for around 6,000 years, and it's currently about magnitude 11. The wider view of the south around midnight. So astrophotographers have had some field days over the last few weeks, field nights, I guess we could call it, imaging galaxies. Ian mentioned last time that our spring is sometimes called galaxy season, but they've also been imaging globular clusters, nebulae, and double stars in the past few weeks. And I don't need to remind you, there are lots of galaxies in this region, the so-called realm of the galaxies stretching north from Virgo. But as I mentioned, the twilight is a problem in imaging them. Here are a few images taken by members. I'm not saying anything more than just credit the observers, Andrew Farrow, Nigel Goodman, galaxies in Virgo and Canis Venatici, M51, also in Canis Venatici. Mark Phillips produced this nice image of Caldwell 5 in Camelopardalis, forget it, and a really good image of Caldwell 3 in Draco, a more edge-on galaxy. I'll resist the temptation to say much more about them. Check the Society's Flickr pages if you want more information. I want to focus now on a couple of objects in this region, Corona Borealis, which lies north and east, above and to the left of Arcturus at midnight in the middle of the month. This is a view of Corona Borealis from Stellarium, showing the coronet or semicircle of stars. The brightest star here is this one, Alphecca, magnitude 2.2. Its name comes from the Arabic for the bright star of the broken ring. It's also called Gemma, a Latin for jewel, and you can imagine this being a coronet with diamonds and things in the coronet. It's an eclipsing binary star, not very dissimilar to Algol, though the brightness variation is too small to be seen with the naked eye. The two stars that make up Alphecca are orbiting each other every 17 days. More interesting is this star, which is a variable star called R Coronae Borealis. And this is a bit like a reverse nova. Normally it's bright, but occasionally it dims. And the light curve from AAVSO, American Association of Variable Star Observers, is shown here. This is a plot of its brightness. It's a very rare type of eruptive variable star. And it was the first one of its type to be discovered by the English amateur astronomer, Edward Pigott, back in 1795. Normally it's bright, but with a low amplitude pulsation in brightness. Occasionally, though, it fades spectacularly, down to by 1 to 9 magnitudes, a bit like a reverse nova or antinova, if you like. And so when it's there, when it's normal, you can see it with the naked eye. It's very easy in binoculars. When it's reaching at its faintest, you need quite a decent telescope to spot it. And it's easy to find because it's the brightest star within the semicircle of Corona Borealis. This shows a long stretch of visibility from 1990 to the summer of 2007, when it dipped and stayed faint. There was a deep fade to magnitude 15, about as faint as we've ever seen it. It's dropped a factor of 4,000 in brightness, and then it started to brighten, but with some large variations. This is a track of its brightness from 2005 to the present day. showing that it's gradually reached back to magnitude 6, its normal brightness. What seems to be happening is that this is a giant star around 10,000 times as bright as the sun, 85 times wider than the sun, but less massive than the sun, surprisingly. And in its atmosphere, you've got carbon, and every now and again, this carbon can condense. You get clouds of soot, and this spreads around the star and hides its light. And then eventually, the light from the star blows this away, this soot away by radiation pressure, and the star returns to normal. So that's where it is, right in the semicircle of Corona Borealis. But it's not the only remarkable variable star in Corona Borealis. We also have T Corona Borealis, which is there, just outside the southern part of the arc. This was first reported as a bright nova by the Irish astronomer John Birmingham in 1866, when it reached magnitude 2, which is brighter than Alphecca. Here we are, Alphecca. It became brighter than Alphecca. Before the outburst, it was a faint, unremarkable 10th magnitude star. But as with Nova Cassiopeia, this is actually a binary star with a white dwarf and an accretion disk and a companion star from which material is being drawn. Another eruption occurred of this system in 1946, 80 years out after the first outburst in 1866. So if we can reckon from that, there's got approximately an 80-year period between outbursts, and we reckon 80 years from 1946, we get to 2026. So it could be about to blow again. So it's definitely worth watching Corona Borealis whenever you get the chance. This is a light curve of the outburst in 1946, and you'll notice that it's a very rapid variation. It brightens from faint to bright in just a couple of days, and then drops almost as quickly back to a low level. And then the outburst was followed by a sort of hiccup a few months later. This is looking east in the middle of the night, in the middle of the month. I'm almost reached the end of the talk, but in the east, we've got the Summer Triangle. I'm sure we'll be focusing on that in future months. There are lots of interesting globular clusters of stars in this area, including M10 and M12, which are here in Ophiuchus, and also M5 in Serpens, which is about there. Perhaps the most famous globular cluster is in the keystone of Hercules, M13, and not far away is M92. Nigel Goodman imaged recently M13, and Hugh Somerville took this image of M92, and both of them are posted recently onto our Flickr group. So that's all I got for you this month.
Brilliant, Alan. As always, can we thank Alan? That was really good.
Thanks very much.
Pleasure. Well, for people on YouTube, I'm sorry, that's the end of proceedings for tonight. We're going to have a short members presentation by me on an old telescope. Of course, you're welcome to join us. And if you look on our website, you'll find full details on how to do that and join the society.